Okay, so welcome. This is the first in a series of videos looking at your Moles 1 notes. So what you'll need to do is have your notes, a calculator and a periodic table. The videos are organised by page numbers. So you'll see it says Moles 1 and then it'll give the page numbers that this video covers. And we're going to start by looking at the front cover of the Moles 1 notes. So the first thing we're looking at is the syllabus statements on the front cover. So by the end of the topic, these are all the things that you should be able to do, use and know. So we're looking at page 1 of your notes and we're going to start by looking at the relative molecular mass. Sometimes you'll see this called the RMM or the molar mass, and it is the mass of 1 mole of the compound. We use our formula and our periodic table to work out the RMM. So for example here, calcium hydroxide. I know the formula because calcium is 2 plus and OH is 1 minus, so the formula here CaOH2. If you're struggling with working out formulas, I suggest you look at the first couple of videos on atomic structure again. But this is telling me I've got in every 1 mole of calcium hydroxide, I have 1 mole of calcium, I have 2 moles of oxygens because it's OH2 and 2 moles of hydrogen. So to find the 1 mole, the molar mass of CaOH2, I'm just going to add the individual masses together and I get a total of 74. Now that number will never change because that is the number of grams of 1 mole and it's always therefore going to be a fixed number. You never change that number. So another example, we've got H2SO4. So that's 2 hydrogens, 1 sulfur and 4 oxygens. So that's 2, because that's the 2 hydrogens, plus 1 lot of sulfur, which is 32.1, don't forget the decimal place, and 4 lots of the oxygen, which is 16. So that makes the RMM of sulfuric acid H2SO4 98.1 grams per mole. So that's telling me I've got 98.1 grams in every 1 mole of sulfuric acid. And then we've worked out the rest of those on page 1. So you just need to be careful where you've got the numbers inside the brackets, the numbers outside the brackets. So here, for example, I've got 1 iron, I've got 3 nitrogens, but I've got 9 oxygens because I've got 3 lots of NO3. And you're going to practice more of these in class. And there on page 2 of your notes, we've got our definitions, and it's important that you know what those definitions are and can be able to repeat them in the exam. So, for example, the relative atomic mass is the weighted mean mass of an atom of an element relative to 1/12 the mass of an atom of carbon-12. You do need to be precise on that one. Again, if you want more details on this, you need to look at the atomic structure videos. So we're on page 3 of your notes and we're looking at using moles. Now, 1 mole of a substance is a fixed number of things of that substance. It's a bit like a dozen. So if I said to somebody I have 1 dozen of something, you would immediately know that I have 12 of those things. Now it doesn't matter if it's 12 elephants or 12 cupcakes. 1 dozen equals 12 things. Well, the mole is a very, very similar concept. 1 mole is a fixed number of things. It's just because atoms are so small and weigh so little, the number of things is very, very large. So 1 dozen equals 12. 1 mole equals 6.023 times 10 to the 23. But the concept is exactly the same. Now you need to get comfortable with using moles in all sorts of calculations, both in inorganic and organic chemistry. And there are some formulas that you need to learn. So the number of moles of atoms is the mass divided by the RAM or the RMM. So that's the mass of 1 mole. the other way you can work out the formula is by using the units. So mass is measured in grams. RMM or RAM is grams per mole. These two cancel, this comes to the top, and this just equals moles. So mass divided by RMM, you can use it here, we're just putting in units, and it will equal moles. But you do need to know that formula, and you need to be able to interconvert. So let's have a look at the first example. Using the relative atomic masses, calculate the number of moles of 100 grams of iron atoms. Well, we know that 1 mole of iron atoms equals 55.8 grams. How do I know that? Because I look it up on my periodic table. So 100 grams would be the mass, 100, divided by the RAM, which is 55.8, and I get 1.79 moles. So 100 grams of iron atoms is 1.79 moles of iron atoms. So there are the rest of the calculations on page 3. You do need to be careful to realise when you're talking about atoms and when you're talking about molecules. So 8 grams of bromine atoms, well, I'm dividing by the RAM of bromine, 79.9. But 8 grams of bromine molecules, well, you've got a Br2 molecule, so its RMM is 2 times 79.9. In other words, there are half the number of bromine molecules as there are bromine atoms in 8 grams. We also need to do this the other way around. So if we're given the number of moles of something, we need to find the mass. So we're just going to rearrange the equation at the top. So mass equals moles times RMM. Again, if I want to use formulas, well, moles times grams per mole. These two cancel, and that equals grams, which is mass. So let's look at an example. 2 moles of carbon. Well, 1 mole of carbon weighs 12 grams. That's the RMM or RAM. And the number of moles is 2. So 2 moles of carbon is 24 grams. And again, we've worked those out there for you. Do be careful when you've got, obviously, molecules here, NH3, that we're working out the RMM. So the RMM of NH3, 1 nitrogen and 3 hydrogens is 17, and I've got half a mole of it, so that will be 8.5 grams. Now, the reason we need to work in moles is because when we look at this equation, it's a molar ratio equation. These are given in ratios of moles, not ratios of masses. So what this equation is actually telling me is that 1 mole of methane needs 2 moles of oxygen. It's not telling me that 1 gram needs 2 grams or anything else. The equations are always written in molar ratios. So that's why I need to work in moles. So what I've been asked to work out is the mass of carbon dioxide produced when 64 grams of methane is burnt in air. Well, I know the molar ratio between methane and carbon dioxide is 1 to 1, because there's an imaginary 1 in front of each of those two. So if I know the number of moles of methane, I will be able to work out the number of moles and hence the mass of carbon dioxide. So I've been given 64 grams of methane. Well, the RMM of methane is 16 grams per mole, 1 carbon and 4 oxygens. So the number of moles of methane is mass, 64, divided by the RMM, which is 16, which gives me 4 moles. Because this is written in molar ratios, I know that 1 mole of methane has 1 mole of carbon dioxide being produced. So it's a 1 to 1 molar ratio. Therefore, the number of moles of carbon dioxide being produced is going to be 4.0 moles. Because if I've got 4 moles of methane, I will have 4 moles of carbon dioxide, and so on. The mass of carbon dioxide produced is moles times RMM, so it's 4.0 times 44, which is the RMM of carbon dioxide, and I get 176 grams. So if I burnt 64 grams of methane, I would get 176 grams of carbon dioxide. So we're going to go through a couple of questions as examples. So the first one we're looking at is the thermal decomposition of calcium carbonate. So calcium carbonate has the formula CaCO3. It's decomposed on heating to form calcium oxide and carbon dioxide. So there I've got my balanced equation. Now I want to know what mass of calcium oxide would be obtained if I thermically decomposed 5 grams of calcium carbonate. Well, the RMM of calcium carbonate is 100.1 grams per mole. Therefore, the moles of calcium carbonate that I've got is 5.00 divided by 100.1, and that gives me 0.04995. The molar ratio, remember these equations are written in molar ratios. Well, the ratio between the calcium carbonate and the calcium oxide is 1:1. So therefore, if I thermically decompose 0.04995 moles of calcium carbonate, I will get the same number of moles of calcium oxide. Now the RMM of calcium oxide is 56.1. Therefore, the mass is my moles, 0.04995 times 56.1, and that gives me 2.80 grams. And I'm giving my answer to 3 sig figs because my data is given to 3 sig figs. So the last example we're going to use is iron reacting with oxygen to form iron 3 oxide. Notice the Roman numeral here is telling me that the iron is in its +3 oxidation state. So I have iron reacting with oxygen to form Fe2O3. And I need to balance this. Well, I've got an odd number of oxygens here, so I'm going to need to balance those out. So if I put a 2 in front of here and a 3 there, that balances my oxygens, and then I've got 4 ions. So I've got a 4:3:2 ratio. I could very easily just have 2, 1.5 and 1, but it's the same ratio. Remember again, these are not masses, these are molar ratios. So the RMM of iron is 55.8. The moles of iron is my mass divided by my RMM. Notice this doesn't come into this part of the calculation at all. Remember, the RMM of iron is fixed. It's never going to change. It's the mass of 1 mole of it. This equation is not telling me anything about the amounts of each of these I have present. It only tells me the molar ratio in which they react. So the moles of iron is mass divided by the RMM, and that equals 0.10035. Now, the ratio of iron to iron oxide is 4:2 or 2:1. Ratio is going to be the same, whether I do 4:2 or 2:1. I'm going to simplify it to a 2:1 molar ratio. So therefore, for every 1 mole of iron, I have half a mole of iron oxide being produced, because 2:1 is the same as 1:1/2. So if I have this many moles of iron, I'm going to have half the amount of iron 3 oxide being produced. So I have 0.10035 divided by 2, which equals 0.050175. I can probably keep all of those numbers in my calculator, I'm just writing them out for the moment. So the RMM of iron 3 oxide is 159.6, so the mass is the mass of 1 mole, so the RMM, times the number of moles that I have, which I've just worked out, and that equals 8.0 grams to 2 sig figs. The reason I'm giving my answer there to 2 sig figs is I've got to relate it back to the data, and the data is given to 2 sig figs, so I can only give my answer to 2 sig figs. So that finishes this first little video just looking at moles 1. And in this video we've looked at the mole and we've looked at the equation moles equals mass divided by RMM. We've also used the equation and a balanced equation to work out reacting masses in a calculation. And you need to be comfortable with doing all of those things. So the key to doing that is to practice lots of them. So we'll give you lots of practice in class. But until then, stay safe, take care, bye-bye.